All right, well, welcome to another fun-filled day of vector calculus. Um, the plan today is to show you how we deal with non-conservative vector fields, like when we want to calculate work and flux over a non-conservative vector field. We're going to see what the approach is with those. Specifically, we're going to be looking at how we deal with them over a closed path. So if we've got a closed path, even if it is non-conservative, we have some tricks we can pull that are kind of handy. So that's what I'm going to show you today. It's a thing called green serum. But before we go there, any questions on the homework or anything else we've talked about? Just a reminder you, homework, there is a set due tonight at midnight. Wow, you guys are full of surprises today. So I'm not seeing any questions and I'm not hearing any questions. So I guess that means we'll go to the whiteboard. You guys are just like all raring to go. You want to know all about green serum, huh? No, either that or the homework is really easy. Okay, so I'll be back with you guys in just one moment. All right. So last time we learned all about the loveliness that is conservative vector fields, right? When vector fields are conservative, we saw all kinds of great things about them. One, line integrals, it doesn't matter how you get there from point A to point B. Only mattered where you started and where you ended. We saw that if we did a line integral over a closed loop, then that work integral gave us 0. And we saw that anyway, we're doing one of these things, we could always use the fundamental theorem of line integrals, which said, if you find the potential function for the conservative vector field, you can evaluate that potential function at the starting point and the end points, and then just take a subtraction of those values, and that got you your line integral. So conservative are awesome. Awesome, 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 awesome. However, we don't always have conservative. And so what we'd like are some tricks, some ways of dealing with these things when we don't have conservative vector fields. So we're going to be looking at specifically doing integrals over a curve, over a closed curve with a non-conservative vector field. All right, so we're going to be doing a good old closed interval. So we're going to put the little circle on there. Good old f dot TDS. So let's look at line integrals. And specifically, we're going to say f is not conservative. Because if f is conservative, this is a stupid thing to ask. Well, not stupid, but it's stupid easy. Because what would the answer be to this if f were conservative?
0.
Yeah, just good old 0, right? You're done. It's a closed path. We got nothing more to do. All right, but of course, if it's not conservative, now we got to try to figure out something different to do. Well, here comes Green's theorem. Okay, so what we're going to use here is this thing called Green's theorem, developed by a mathematician by the name of Green. And it goes something like this. So first of all of the conditions, there are quite a few conditions that we need to have. Okay, so first, we need to have a region R that is simply connected. So before we move on to the next piece, do you remember what that means? Simply connected?
No beginning, no end. Or the beginning is the end.
Okay, so the beginning has to be the end, so we're closed. And I saw there, Victor just put there like no holes, no loops, right? Like it's not crossing. If we have a curve, it can't be crossing itself. There can't be holes, things like that. So it's just a good old read, one big chunk that's got a nice boundary to it, right? Okay, so it needs to be simply connected region. It has to have a smooth boundary that we're going to call C. Okay, so smooth is what you think. Smooth curves, you've been into that many times through calculus. Smooth just means the derivatives exist and things like that. So it's a nice smooth curve, no sharp turns, no things like that. We're going to see that the smoothness we can kind of get around. All right, but it needs to be a smooth boundary, and it needs to be oriented counterclockwise. And that's exactly what it sounds like. If I've got some sort of a region here, let me draw one with a curve. Okay, so this is R. C, of course, is the curve itself out here. But in terms of its orientation, right, you can have all kinds of different orientations for curves. Really, there are two, right? So we could be going around this clockwise or counterclockwise. We need to be oriented counterclockwise. Do you remember what happens with line integrals, the work integrals, if you switch the direction of travel? You remember what happens?
Sign changes.
Yeah, it just changes sign, right? So it's really easy if you've got one that's oriented clockwise. Well, you can still use Green's theorem, but then just change the sign. But what I'm going to show you for Green's theorem requires counterclockwise orientation. We actually have another way of saying that, this oriented counterclockwise. We say that this is positive orientation. So if you ever see that, positive orientation versus negative orientation. Positive orientation just means that you're going clockwise around or counterclockwise around the boundary. Another way to think about it is you're positively oriented if your left side is always pointing towards the interior of the region. That's also positive orientation. It means the same thing. Just because sometimes clockwise, counterclockwise doesn't really work so well, or it's a little more confusing. We just say it's positive orientation. Okay, so simply connected region, smooth boundary C, that's oriented counterclockwise. All right, and then we need one more thing. I told you there's a lot of conditions here. And let F hold on. I'm going to try to do it. I'm gonna lapse at some point. I'm going to try really hard to stay with the book. PQ. All right. If I go to MN, just realize that that's what I learned decades ago, and that's my standard. But I'm going to try to go PQ like the book. Okay. So we've got our field that's PQ, where P and Q, where those two components, they have continuous partial derivatives. And these continuous partial derivatives, and it's over the region R. Like, I don't care what's going on. Like, if the vector field out here has some discontinuities with the derivatives, I don't really care. I just need to make sure that in this region, these guys P and Q have nice continuous partial derivatives. Okay, so this is all the setup. This is what we have to have in order to use Green's theorem. So let me give you the then bit. Okay, so if all of this is true, and then this is the big deal. All right, so then the integral of f dotted with t ds we can also think of this, I don't know that I actually showed you this, but it's called the differential form of a line integral. But it would look like p dx plus q dy. Okay, so it's just another way of seeing the line integral. But this guy is actually equal to a double integral over the region of qx minus py. Okay, so here's the deal. What Green's theorem does is it takes a line integral and it turns it into a double integral. So basically, this is a way of linking this new kind of integral back to one that we already know. And there are instances where that double integral is going to be easier to do than the line integral. And if that's the case, we can go ahead and use Green's theorem, again, assuming we have all of this. And it turns out, we'll see in a little bit, excuse me, that sometimes you can actually use Green's theorem to help you with double integrals. Instead of actually calculating a double integral, you can turn it into a line integral. And sometimes that's faster. Okay, so this is just a link between these two types of integrals, line integrals and double. All right, so yeah, so far so good. Ish. All right, but here's the deal. Got to kind of show you why this is. Now, I'm not going to be really rigorous with this proof, because if we tried to do it like math lawyer style, connect all the dots, dot all the I's, cross all the T's, it's going to go over your head. It's well beyond the scope of this class, but we can kind of build the framework for how this works, and you can kind of see kind of how this plays out. Okay, so what I'm going to give you is a partial proof that's got a lot of hand waving. Okay, but it's going to give you the general feel for how this comes about and why a line integral is actually the same as a double integral when we're in this form. Okay, excuse me. So here's how we're going to approach this. Imagine that our region is such that we can kind of split it this way. So here's our region. Excuse me. And what I'm going to do is I'm actually going to split it into two curves. So there's going to be the red curve that forms basically the right-hand side of the shape. And then I'll have a blue curve that is the left-hand side of the shape. So we can kind of think of it as these two different functions. They are functions of y because they're sideways. But let's just say that this one that's on the right, this is f2 of y, and the one that's on the left is f1 of y. Excuse me. All right. So we've got this kind of shape. So what I'm going to do is I'm actually going to show you that the line integral over these two pieces is going to be equal to double integral piece. So basically, we're going to equate those together. But really, I'm just looking at this portion right now. Remember how there are two pieces to this integral? And there were two pieces if we write this in the differential form. I'm going to show you how this q dy integral is actually equal to the double integral part of the qx. And then I'll show you how we would set it up to prove the other half and connect it up. Real quick, I wrote this and I just kind of said, oh, hey, this is the differential form. It is. And that might have felt a little bit weird. Let me really quickly show you where this comes from. So remember the whole f dot t ds. You can think of that as the ds is a got your little differential chunk in there. The dt, we can transfer it to a dt. So think about when you do the dot product, you're taking the first component of f, which is p, and you're dotting it with the first component of t ds. Well, that t ds piece gives you the dx. And then the second component when you dot it is the q times dy. So that's actually where that comes from, just FYI. Okay, well, let's come back and let's actually look at these integrals. All right, so let's start with the line integral. You can now think of this as we're doing a line integral over C1. Remember, we're oriented in a counterclockwise direction. So actually, no, let me call this one C2. And this guy is C1. So we just have these two curves. We break it into the two. And let's think about doing the line integrals over those two curves. So if we just look at the q dy piece, we're looking at the integral over c of q dy. That's going to be the integral over c1 of q dy plus the integral of c2 times q dy. The good old, you can take an integral, break it into two pieces, right? So we've got those two chunks. All right, so what we want to do now is basically parameterize these curves. Well, the easiest way to do that would be call x equal or y equal t, and then x is going to equal f2 of t or f1 of t, right? And so let's look at what that's going to be. We'll look specifically for C2. The parameterization for C2, we're going to make it f2 of t comma t. Excuse me. So I'm letting y be t, and if I let y be t, then this is the x component. So think about what we need then. We need q, right? We need a q dy. So let's think about what that's going to be. Well, if I set this thing up, and similarly, this one will be f1 of t, comma t. So if I set this up as an integral from t value to t value, so from a to b now, we're going to integrate from a to b. And what we're going to get, think here's a, here's b. Because remember, it's y values are my t, so from a to b. I'm going to get the integral of the q at f of 2 minus the q f of 1. So real quick, what I'm doing here is I'm changing my q in terms of the parameterization, right? We're substituting in for the x and the y. That's all I'm saying here. But now the question is, why did one of these get a minus sign? And specifically, why did the f1 get a minus sign? Do you see why?
It's like top minus bottom, except oriented with respect to the x-axis.
Kind of. I mean, it turns out that it worked out that way, but that's not why I did that here. That's actually going to be our next step, Bradley. That's what's going to get us to our double integral thing. Think about this. Remember what a and b are? They're y values. I'm going from a to b. Yeah, on the one, I'm going up. And the other, I'm going down. So on this green, or this kind of teal, bluish green one, I'm going backwards. I'm going from B to A instead of from A to B. And so because I'm going in the opposite order, I have to change the sign to make these bounds match. All right, so this is what the line integral piece is going to give. At least this is the line integral of q dy. And what I'm going to show you is that's actually equal to the double integral of qx dA. So let's look at that part now. I'm going to erase green serum. I'm going to put it back up in a second. I need the space here. But now what I want to look at is the double integral over this region of the qx dA. So think about defining this region with integral man. Integral man is going to be much easier to set up integral man if we've got integral man sideways. Right? If we do integral man sideways, this will be a little bit easier. So the bounds on that then, if we look at this region with him sideways, that means we need to start with a dx, and then we're going to go to a dy. In terms of the x's, excuse me, his feet are at f1 of y, and his head is at f2 of y. And then the y's go from a to b. So that's what that double integral would look like. Or the easiest way to set up that double integral. All right, well, let's integrate now. So we're going to start by integrating qx with respect to x. So if you take a partial derivative with respect to x and integrate with respect to x, what do you get?
X. Q, X, X.
You're going to get q, right? This is the derivative of q with respect to x, that if I integrate with respect to x, brings me back to q. So that one, when we integrate, we're going to get just plain old q evaluated at f1 and f2. dy. All right, so if I now plug in bounds there, I get the integral from a to b of q at f2 of y minus q at f1 of y dy. And if you look really closely at these two things, you'll spot only one difference in them. That one difference is this uses the letter T, this uses the letter Y. Big deal. These are equal. Okay, so what we know at this point is this is like half of the green serum proof. This is the part that's using the second component of the line integral and showing that it's equal to the first part of the double integral. Now, there was another piece to this, right? We had the p dx plus q dy. And then in the double integral bit, we had qx minus py. Well, if you do the line integral on the p dx, you'll see that it actually equals that double integral of the negative py dy. And you actually prove that in a similar way. Instead of thinking about your region as a sideways region, do it vertically. So you've got a top and a bottom, and you're integrating from a to b on the x. And you'll see that the other piece falls out. Okay, so this is like half of the proof, not very formal, but it's giving you kind of the basic idea of why this works. Okay, so Green's theorem is 100% accurate, always works. It has been proven using this kind of idea. All right, so if this whole bit just went over your head, that's okay, don't worry about it. I wanted to show you where it comes from. Really what you're going to need to be able to do is to use it. So let me show you how you use it. So we're going to go back to an old friend that we saw quite some time ago. We're going to look at the field that's given by y comma negative x. So I think this was the first field that I ever showed you that wasn't conservative. Remember the check, it's really easy to see. Take a derivative of the first component with respect to x, the second component with respect to y. Do you get the same thing? No, one's 1, one's -1. So we know that it's not conservative. Now, the path that we're going to use is the circle. We're going to do a unit circle path. Okay, so we're going to go ahead and start here at 1, 0. And we'll follow this around counterclockwise so that we're in a positive orientation so that we can use Green's theorem. It is a simply connected curve, so we know we're all good there. But let's see if we can calculate how much work is done going around this path. Now, if this had been a conservative field, like if it had been y comma x, answer's done, 0, right? It's conservative. But it's not conservative, which means we actually have to use Green's theorem. So here's what we want to do, right? Green's theorem again says if we do this integral over our curve, we've got the f dotted TDS. It's the same as the double integral over the region, this region, of qx minus py dx. And I hate this. Every time I write this, I have to translate in my head what letters go where. So anyway. All right, so this is what we're going to use. So let's get Qx and Py. So remember how this plays out for this field. P, well, that's y. And Q is negative x. All right, so let's set this thing up. So we're still going to be integrating over the region. We'll worry about that later, but let's first get the function that we need to integrate. So we need Qx. So Qx is -1. And then we need Py, which is -1 dA. So we're going to be integrating over this region the function -2. So before we go any further, just take a gander at that. This is going to be a really nice integral. Super easy to do. I don't care if we do it at dx, dy, dy, dx. It's just -2. Piece of cake. Think about the alternative. If we had done the line integral, what would we have had to do? Well, we got to parameterize the curve. Well, it's not terrible because it's a unit circle. We've done it a bajillion times, but we'd have to parameterize it. Then, yeah, thank you, Victor. Then we'd have to differentiate it to get r prime. We'd also have to change our field in terms of that parameterization. Then we'd have to do the dot product. Then we'd have to integrate. So we'd also have to have t values to correspond to going over the entire curve. So it requires a bit, right? Again, this one's pretty nice because it's a super easy parameterization. But think about those times we've had curves that were not so fast to parameterize. Instead, I took a couple of partials, no problem, that's fast. And this form, I mean, this turned out to be a really nice form because it's just -2. I'm not gonna have to like substitute anything in, no change for anything for this. Okay, now let's go ahead and calculate this integral. So how are you gonna want to do this integral? What's it begging for?
Show me the polar.
Yeah, definitely polar, right? It's a nice circle. So if we were going to set this sucker up in polar, it's going to be the double integral -2 r dr d theta. The r's go from 0 to 1. The thetas go from 0 to 2 pi, which is also a very easy thing to calculate. So go ahead and do that calculation. And yeah, you get what you get. It actually should be -2 pi. All right, so now what we know is that if we've got this particle, and we're going to move it on this path in this field, the field is going to do negative work. That means that the field lines overall are pushing against the direction of travel. So if we're thinking about this field as current, let's say in water, it's pushing against us more. That's why it's a negative number. Now, I'm not saying it's always pushing against us. I don't know that necessarily, but I know that overall it pushes against us more than it pushes with us. Okay, it's doing negative work. Okay, so hopefully this example shows you how nice green serum actually is, because it took it from some kind of some sort of curve we're going to have to parameterize, blah, 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 to a super simple integral. Let me actually show you another shortcut even here. When we got to this -2 dA, I mean, it wasn't terrible. Setting this thing up in polar is pretty fast. The integral is easy. Right? You just get -r². excuse me, plug in your 1 and 0, whatever, it's fast. But it's even faster if you recognize this. Okay, so in general, let's say we've got a C times dA here. So that C can come out. So we're going to have some constant times the double integral over the region of dA. Well, do you remember what that gives you? What you get if you do a double integral of dA?
1.
Area.
Yeah, the area.
It's the area, yeah. So this is going to be C times the area of R. So check this one out. We had -2 dA. So this is just, excuse me, just equals -2 times the area. Well, this is a circle of radius 1. So it's -2 pi. So keep on the eye out for that. Keep your eyes open for that as well. Keep on the lookout. Because if you're ever integrating just a constant in a double integral, you can just multiply it by the area and be done with it. And sometimes that's faster. All right, so how are we feeling about this? Is it at least a little intriguing?
Yeah.
You can see maybe it can work. Okay, so I see in the chat box, Victor, you said, what if F, excuse me, is R cubed? What do you mean by that?
I think he means 3-dimensional.
Oh. Okay, I gotcha. Thank you. That makes total sense. All right, so if we're dealing with 3 dimensions, you can't use Green's theorem. Sorry. However, there's a flip side to that, and you know what that's going to be, right?
There's a
When we're in
different way.
3 dimensions, there's going to be a different theorem that applies to 3-dimensional creatures. So in terms of if it's 3D, technically, nope, Green's theorem doesn't apply. We're going to have to figure out something else that will do sort of the equivalent in 3 dimensions. So think about what the equivalent in 3 dimensions is going to be.
I guess that it's Stokes' theorem.
I mean, it could be. We still got a couple more theorems to go, and Stokes is one of them. But if you think about, like, if we extend this out a dimension, right, we're going to have to add in a third piece. So there's going to be a P, a Q, and an R, or in my language, an M, N, and a P. But you're going to have 3 components of it. So your field's going to have 3 dimensions. But then instead of having a 2-dimensional curve, we're going to need a 3-dimensional surface. So if we've got a 3-dimensional surface, it's going to have something to do with the region that it encloses. Well, that's now going to be 3-dimensional, which means it'll be a triple integral. So you'll see that there's a very similar thing to Green's theorem that extends up to what we call a surface integral. Now, we haven't talked about those yet. So when we get to that, we'll see surface integrals, and surface integrals are going to be related to triple integrals, just extending it out a dimension. But anyway, so for right now, we're 2D. Only 2D. This only ever works in 2D. But good question, and hopefully that is a good enough explanation. For right now, just Green's theorem only works 2 dimensions. All right, any other questions about this one before I show you another example? No, we're good? All right, so let's try another one here. And this time, we're going to change the field and we're going to change the curve. Okay, so let's go with our field as x minus xy So that's the x component of it. And then the y component of it is y squared. Okay, so there's our field. And then here's the path that we're going to travel. So this time it's going to be rectangular. Okay, so it's going to be a rectangular path. We're going to go from 0, 0 out here to 4, 0, then up to 4, 6, then over to 4, 6, or sorry, 0, 6, and then back to the origin. But we're going to go ahead and orient ourselves positively so that we're going in a counterclockwise direction. So that's C. And again, what I'm looking for is what is the integral over C of f dotted t ds. And since it's closed, I'll go ahead and put the circle on there. All right, so let's think about this as a just straight up line integral. Could you do this without Green's theorem?
Yes.
Yeah? What would it entail? What would you have to do?
I'd have to do it in 4 different integrals.
Yep, we'd have to break this curve into the 4 different pieces, right? We've got 1, 2, 3, 4. Do those 4 line integrals separately. Luckily, the parameterizations are pretty easy since they're either vertical or horizontal lines. But regardless, we'd have to do the 4 of them and then add them. All right, instead, we can use Green's theorem. So let's do that. Let's look at the double integral over that region. And let's start with what we have to integrate. Okay, so again, remember what we got to do. We got to take the partials of P and Q. So we're going to start with the partial of Q with respect to X. All right, well, what is the partial of Q with X? So that's just 0, good. And then we're going to subtract from that the derivative of P with respect to Y.
Negative X.
Which is going to be a negative X, good. So we had 0 minus negative X dA. So we're integrating X dA. Now, we weren't quite as fortunate this time. Excuse me, X is not a constant. So we can't just do that constant times the area of this region. But this is actually a really simple double integral to set up. So which way do you guys want to go? Y first or X first? Because I really don't care.
Why?
Well, because we got to pick something.
No.
I know it's been a long time since I pulled that one. All right.
You were waiting for that.
Let's go dy dx. Oh yeah, that's one of those stock ones that's always in there waiting for the perfect opportunity. So thanks for that, Bradley. All right, so we go dy dx, then what are the bounds on y?
0 to 6.
There you go, 0 to 6. And then the x's give us what, 0 to 4. So one integral, an easy integral, right? You love double integrals that look like this. It's going to be way faster than trying to do the 4 separate line integrals, right? So at this point, yeah, you plug it in. So let's see, we're going to get 6x, which then is going to give us 3x squared, plug in a 4, I think that's 48. You might want to double check my math on that, but I'm pretty sure that it's actually a positive 48. I mean, that integral was so easy I could do it in my head, as opposed to trying to break it down. So think about what this means. Now there is work done, right? Work is done, but it's positive, which means that overall, this field points more in the direction of where we're going than not. Is it always pointing in the direction of where we're going? Don't know. But I do know that more often than not, it's pushing us along. It's helping us along. Okay, so a couple of really quick examples. And what's going to make this tough, or what's going to make this nasty? Really, it's two things. One is if this subtraction of the partials, if the qx minus py, if that's ugly, the integral could be nasty. And also if the region's not fairly nice, right? Like I did a circular region and now we have a rectangular region. If they're nice shapes, triangles, ellipses, things like that, it's going to be fast. Otherwise, well, it's going to be as difficult as setting up a double integral is anyway. But usually, it's way easier to set up that double integral than trying to do the line integrals, trying to parameterize. Right? Like think about some of the regions that we've seen where we've done double integrals. Like, remember when we had one that was kind of shaped like this, where if you do it vertically, you have to do it in two integrals, but horizontally, you need to do it in one. This is only two curves, but trying to parameterize those two to do a line integral might be a little bit more difficult than setting up the double integral. Okay, so take it that's what this is for. Just it helps us in those sorts of situations. All right, so good so far? All right, well, now instead of doing more examples, because you see what you need to do, let me show you some other things that we can do with green serum. So notice that what we did with this definition of green serum was to do work. This was for work. The question is there a way we can apply this to flux? Because that's the other kind of integral that we like to do a lot, right? Is there a flux version of Green's theorem? Well, obviously there's going to be the way I'm setting this up. Yeah, there is a way that we can actually augment this into a flux kind of idea. So let's remind ourselves about flux, at least what the integral looks like. So for a flux integral, how did we set those up? We're going to still do it over a closed path. So I'm going to integrate over a curve C. But what goes into the flux integral?
F dotted with n.
Okay, good. So it's not F dotted with T anymore. It's F dotted with N. All right, but we saw that there was a way to get N, right? Because if it's two-dimensional, remember we're two-dimensional, there's a total shortcut. What is that shortcut?
Dot it with little n.
Okay, so instead we can use that little n, which is as Victor just said there, we flip the prime and we change the signs, right? So we change the sign on one of them, and we saw what we did is we changed the sign on the x. Okay, so think about how this was playing out for the work integral. Let me go ahead and rewrite Green's theorem here. It was F dotted with T ds. And so it was the double integral of the region of Qx minus Py. Okay, well, let's just think about what we're going to do. If we're going to do a flux integral, we're going to use that whole swap the partials and make one negative. Okay, so if we swap those partials, instead of a q with respect to x, this is going to be Q with respect to Y. And instead of P with respect to Y, it's going to be P with respect to X. That comes from the swapping. And then we have to change the sign. Well, it turns out we changed the sign on the P. Remember, we make the x1 negative. So in terms of the flux integral and the form for Green's theorem, we're still integrating over R, but now it's going to be Px plus Qy dA. And that solely comes from that swap, change the sign thing that we did before. So they look similar for sure, because they're still line integrals, right? They're still line integrals over the closed path. That's why they got similar form, but we're integrating something different when it's flux as opposed to work. But beyond that, it's same old, right? So we have a couple of examples that we've done where we did the line integrals. Well, let's do the flux integrals on them. So since I've got this one handy, let's take a look at this guy. So now let's calculate the flux over the curve. All right, so we're still going to do a double integral over this region, but now we need Px plus Qy. So Px is going to be 1 minus y. Qy is 2y. So we're going to be integrating over this region 1 plus y dA. Well, the region is still rectangular, so we can still set up that integral just as easily as we did before. So I think we did it a dy dx, doesn't really matter. The y's went from 0 to 6, the x's went from 0 to 4. Okay, so let's see, 1824 times 4, I think, is 96. You should definitely double check me on that one. But I'm pretty sure that that's 96. All right, so the question is, what does that mean in terms of the flux? Now, we've seen positive flux and negative flux just means opposite directions, right? So a 96 versus a negative 96 would just mean flow's going one way or the other. But specifically for this, what does this mean in terms of flow? Is there more going out or more coming in? Well, this is now where the orientation matters. Since we're going around in a counterclockwise direction, our ends, the way that we've set them up, the ends are always pointing outward. Which means if we get a positive flux, that means more is going out. Okay, so this just means it's out. So for this field, whatever this field looks like, more is flowing out than flowing in. So in the language of physics and stuff like that, that means that there's a source in here. So if we were talking about like water flow, that would mean that there is a source of water coming in. So there's a spring, there's something that's pumping out water. If we're talking about electrical charge, okay, that means that there's a charge in here. There's something that a charged item, particle, whatever, that's creating this field. Okay, so positive just means that it's going to be going outward when we've got positively oriented boundary curves to simple regions, simply connected regions. If we don't do that, if we now are, say, clockwise, so negative orientation, this would mean something different. That would mean it's pointing in now.
Hey,
Okay.
Bruce.
Yeah.
How do you know that the ends are pointing outwards? Because I thought that the ends point into the center of the osculating circle, but there is no osculating circle with a straight line.
Okay. It's because of how we choose to change the sign. Because remember when we do that trick of swapping the two coordinates and then changing the sign, it can actually be pointing in one direction or the other. And so back in the day, we had to kind of be careful and pay attention to which one it was to actually get our N. Kind of remember that?
Yeah. We had to, yeah, exactly.
So since we're doing this now systematically, where we're always changing the X coordinate, the sign of the X,
changing the X coordinate that we switched to the Y.
Okay, so when I say change, I mean change the sign on.
Right.
Right, because like I don't want to use P and Q because that's just going to confuse us all. But like let's say we had a vector that was Mn. No, I can't use N. Hold on. Okay, we got a vector AB. I think I'm safe if I do AB. We saw that to get the orthogonal, we have to swap them and then change the signs on one.
Mm-hmm.
But what we're doing now is we're always changing the sign on the first one. That's what made it so that these were both plus. And if this is how we're always going to do it, then the vectors are always going to be pointing outward when we're counterclockwise.
Okay.
So if we had decided to go the other way and be negative A, that would have made both of these negative, which then in this example would give us a negative 96, but negative 96 would still mean outward because we're orienting the opposite direction. So like it's kind of nice that it all works out. However you decide to orient yourself, whichever one you decide to switch, but because we're switching the sign on the first one, that's making it so that when we're counterclockwise, positive fluxes outward. And I'm afraid I probably just confused you more.
No, I buy it.
It's just because of the way that mathematicians love having the systematic, here's how we do it, let's set it up so it's always regular kind of deal, right? And since you could be going clockwise or counterclockwise, mathematicians are just like, nope, we're going to go counterclockwise is positive. Boom. And as soon as you define it that way, everything that we're doing falls out. We alternatively could have gone clockwise is positive. The theorems would all look different, but the end results would still be the same. Like if you did all of yours with counterclockwise being positive and I did all of mine with clockwise being positive, at the end of the day, you would say, oh, there's 96 units of flux outward. When I do my calculation, I would tell you the same thing. I'd say, oh yeah, I've got 96 units going outward. You just calculated as a positive 96. I calculated as a negative 96. But it's really the same thing. And this should kind of make sense that it shouldn't matter how you perceive it, because like when we're looking at it on the whiteboard here, and we're saying we're going around in a clock or counterclockwise direction, imagine somebody's on the other side of the whiteboard. Right? It's a transparent whiteboard so they can see it. What are they going to say about its path? Well, they're going to say it's going around clockwise. Right? So they would view it as a different orientation. but the flow should still be the same. Like if you're on the other side, you're still going to say it's going outward, because outward is outward, no matter whether we're looking at this as clockwise or counterclockwise. So I know it's kind of a weird thing to think about, but we just do it so that we're just always the same, always systematic. Positive orientation is counterclockwise. In that case, positive flux means outward, negative flux means inward. Okay, it makes it easier to specify in the one way. All right, so I feel like I've beaten that to death. Just smile and nod. I know I can't see your picture right now, Seamus, but just smile and nod. There you go. Cool. All right. So there would be the flux integral for this one. Let's look at the circle. Let's look at the circle real fast. See what kind of flux we get from that. So let me see if I can remember what we did there. I think that one, we had our field was y negative x. And we were doing the circle like that. Okay, so let's find the flux for this one. So same deal. This time we're going to do the double integral of px plus qy over our region. Okay, so px, the derivative of the first one with respect to x is 0. The qy is also 0. So we're integrating 0. Well, I don't care what region you're over. That's going to give us 0. All right, so what would that mean in the context of like physics, like if this was a water flow kind of thing? What does a flux of 0 tell you?
There's no water going through it.
Not necessarily that there's no water going through it, because there could be water going through it, but anything that's flowing outward gets matched by some flowing in. So the net flow across this would be 0. So if there, and it could be that there isn't any that's going across it. And in fact, with this one, that's exactly what's happening. I don't know if you remember, but this was one where the vectors are always pointing in the opposite direction of the tangents. So there is no perpendicular piece. So there literally is no flow over this. But in general, a 0 just means anything that's coming out is getting balanced by something coming in. And in general, water does this. Since water is not compressible, you can't compact it down very much, like a little bit, but not as compressible as like air. We called it the continuity equation. What goes in comes out. Right? If I start dumping water into like a finite container, if I'm not changing the volume, anything that goes in, there has to be an equivalent amount coming out, right? And so that's kind of the story here of a flux equaling 0. All right, so this guy is kind of interesting because here we have a closed loop and our line integral is 0. It's kind of like work over a conservative field. So this kind of field is the equivalent of a conservative field when it comes to flux. Right? Think about conservative fields. When it came to work, closed path, we got work 0. And it didn't really matter how you get there from point A to point B, blah, blah, blah. Well, this is the same deal, but for flux. All right. And so these have a name. And these are what we call source-free fields. And the name tells you everything. Because remember what a source is. A source, kind of like in that integral, the flux integral we did before this one, the one with the rectangle, there was a source inside of that region. It was producing flow outward. So a source-free field doesn't have those. It doesn't have sources. All right. And basically, here are consequences of source-free fields. We're going to get that the integral of f dotted with n ds is 0 for any closed curve. Just like with the gradient fields, with conservative fields, the integral of f dotted t ds was equal to 0. All right, it turns out that, not closed integral, if you integrate NDS over two different curves, C1 and C2, these are going to be equal if C1 and C2 start and end at the same place. So basically what that means is that it's path independent. Okay, so we saw that with potential, or with the, conservative vector fields. There's also what we call a stream function. So I'm going to call this f of xy. And the stream function, this is the analogous equivalent to the potential function. But this is one where it's not quite the same thing. It's not the gradient of the stream function equals f, but it's similar. It's just that p is equal to fy, like before, and q is equal to negative fx. So same kind of idea. So it's not quite the gradient, but it's the gradient with the x component sign changed. What? The x component sign changed again? Yeah, because that's how we built the whole idea of this n and flux. So these three are virtually, I mean, we made a similar list for potential or for conservative vector fields. It's just, it's slightly different because now we're looking at flux equaling 0. And so there's also a check for this. You may remember that for the conservative vector fields, we looked at the partials of P and Q, and we saw that they were equal. Well, now they're not going to be equal, but for a source-free field, what we know is that P of x plus, hold on. Let me make sure I got my letters right. I think I got that wrong. No, we're good. We're good. We're good. We know that P of x is equal to negative Q of y. So before, for conservative, it was px equals qy. Now they're off in sign. So here's what's kind of cool. If you're going to check to see if a vector field is conservative, and it's not conservative, you've actually already done the check for source free, because you've already done the partials. You just see that they're not equal, they're opposites in sign. If you get the case where they're not equal and they're also not opposites, then it's neither conservative nor source free. But source free is useful in lots of circumstances. Specifically anything where you're looking at flux. So it tends to be big in E&M, electricity and magnetism, and also in actually like fluid physics, specifically atmospheric science. If you do atmospheric science, the air, we have all kinds of great sources and sinks. Weird things happen there because air is compressible. So. All right, so yeah, there you go. We can actually now find stream function. So think about the one that we just did. We saw that this guy, we saw that it was source free. Well, let me show you how you could check that here, right? If you look at px, it's 0, py is equal to 0. Hey, look, they're opposites of each other. It is source free. So we can find the actual stream function. So here's what we know about the stream function. The f, it's the integral of p with respect to y, which is going to give us y squared over 2 plus potentially other stuff with x. We also know that it's the integral of negative x, or sorry, the negative x
Wait, Bruce.
Yeah.
P sub x and P sub y are both 0?
Or sorry, that was q sub y.
Okay.
Sorry about that. Got so excited I wrote p twice. So the stream function, we just put those together. And so we get the stream function of this is x squared over 2 plus y squared over 2. But you can check it. You can see that these two things are the partial with respect to y and then the partial with respect to x. The negative partial with respect to x. All right, so kind of interesting. All right, so cool. We can use Green's theorem for just work integrals. We can now do them for flux integrals. It's just slight variation. But here's the last thing I want to show you that we can use Green's theorem for. You can actually use Green's theorem to find areas. Okay, so this one probably feels a little bit weird, but you know, we can totally figure out the area of something using a line integral. Okay, that's basically what this is saying. Instead of doing a double integral to find the area, we can just use a line integral instead. And there are certain circumstances where that's much easier. All right, well, let me show you how this plays out. So think about how the double integral thing worked out for Green's theorem. So it was qx minus py dA. Well, if we wanted to find the area, what we need is for this bit to equal 1. So if qx minus py is equal to 1, then this is going to give us the area. Okay. So basically what we need to do is create some sort of a field that gives us qx minus py equals 1. So there are a lot of choices for this. Lots of choices. We could go say, here's one option. Option number 1. We can make it where qx equals 1 and py equals 0. Right? Because if qx is 1 and py is 0, then 1 minus 0 is equal to 1. So let's think about what those things would look like. Well, that would make q equal x. And that would make p equal 0. So we could use the field 0, comma x. A second option would be where qx equals 0 and py equals minus 1. So that would make q equal 0 and p equal negative y. So we could use negative y, comma 0. I could do this all day. I'm going to give you one more. This is the other, this is like the, you're going to pick one of these options. It would be that qx is equal to 1/2 and py is equal to minus 1/2. So 1/2 minus negative 1/2 is 1. Well, that makes q equal 1/2 x, p equal minus 1/2 y. And I apologize, I'm running out of space here. But in that case, your f would be minus 1/2 y plus 1/2 x. Let me try to write that a little bit neater. Here's how I'll save a little space. Instead of writing 1/2 y, I'll write y over 2. Okay, so basically what this means is if I've got some sort of a shape and I want to try to find its area, I can do a line integral instead. And I can do a line integral of f dotted with t, or if I've got my parameterization, f dotted with r prime, where I pick f to be one of these three forms, or any other form that makes qx minus py equal 0. All right, so for example, let's find the area of an ellipse. I know we've already done this. I know we already know the formula, but let me show you how we could use Green's theorem to do it. All right, and I'm going to do it in such a way that we make it generic. So let's just do the old ellipse that's coming out here to A, and this one up to B. All right, so what we'd have to do first is parameterize this curve, because we want to do a line integral. Okay, so do you remember the parameterization for an ellipse?
A cosine t, b sine t.
All right, beautiful. So if we look at r prime, that's going to be minus a sine t, b cosine t. So now what we want is to pick one of these forms for f. It doesn't really matter. So I'm actually going to use the third one. You'll see why. Okay, so I'm going to use the f equaling negative y over 2 x over 2. So I need to go to the x and y of my original parameterization. So it'll be minus b sine t over 2, comma, a cosine t over 2. Right, I know using this one that my double integral gives me a 1. All right, so let's do the line integral of f dotted with r prime. We're going to do f dotted with r prime dt, and our t's are going to go from 0 to 2 pi, because that's going to take us all the way around the ellipse one time. So if I take these and I dot them, I get AB, integral from 0 to 2 pi, of AB over 2 sine squared t, that's these two, plus AB over 2 cosine squared t dt. Well, I factor out the AB over 2. I get sine squared plus cosine squared, which is 1. So this is AB over 2 times 2 pi, which is pi AB, which is like the second time in as many weeks that I've shown you what the formula is for the area of an ellipse. And possibly the third or fourth time you've ever seen finding the area of an ellipse, but in a different way. So we were actually able to use a line integral. Think about that. We were able to use a line integral, adding stuff up over this curve, to get the area of the region enclosed by it.
Yeah, it's pretty crazy.
That's very crazy. But that is the power of Green's theorem. Is Green's theorem now relates double integrals to line integrals. So anything we did with line integrals, we can do with double integrals. Anything we did with double integrals, we can do with line integrals. They're kind of related to each other in this weird sort of way. Doesn't seem like they should be, but they are. Anyway, so there you go. There's Green's theorem. It's kind of cool and super, super useful in lots of situations. All right, well, it looks like we're pretty much out of time, so I'm going to stop here. Next time, we'll talk a little bit more about Green's theorem, talk about what do we do if we don't have a simply connected region. Can we still use Green's theorem? And the answer is yes. It's not going to surprise you what we do. We break things up into simply connected regions and then go from there. But we'll kind of formalize that talk. And then we'll keep moving forward. And just so you know, for the next little bit, like I was mentioning earlier, I think off the record, we're in the home stretch. We have Friday, next week, which includes an exam. Then we're off for a week for Thanksgiving. Then we're back for a week, last week of class, and then finals. So we really have 2 weeks and just a little bit left. So we're in the home stretch, but we're doing great on time. We just have a few more things to talk about. I'm going to need to introduce you to surface integrals, which are three-dimensional equivalents of line integrals. Instead of adding things up over a curve, we're going to be adding things up over a surface. And then I'm going to introduce you to a theorem that relates surface integrals to triple integrals. Definitely hinted at that earlier today with Victor's question. And then we have one more theorem that kind of links surface integrals and line integrals. So that's where we are. That's where we're heading. Again, no quiz on Friday. since this was a short week. So we won't have anything there. The next assessment thing will be an exam, which is a week from Friday. We'll talk more about that coming up here. All right, so with that, I'm gonna wish you all a great couple days and stop the recording.